This is the last lecture of chapter 4. Before we get into it, however, let us do a quick review of what we covered in the previous lecture. We looked at alkanes and a way of representing alkanes in 2 dimensions. Remember that these molecules are in 3 dimensions. We discovered that there were 2 ways. One is the dashed wedge, where we use dashed lines and wedges to indicate if they are in the plane or behind the plane or in front of the plane. Next, we looked at another representation, which is the Newman projection. This involves looking directly down a carbon-carbon bond and just describing what one sees. Next, we looked at conformers and relative energies. So in other words, we use the energy profile to place different conformers of the same molecule on the energy profile to indicate their relative stabilities. And lastly, we looked at the cis-trans isomers of cycloalkanes, specifically cyclopropane, cyclobutane, and cyclopentane. Let's go into today's lecture. In today's lecture, what we'll cover is conformers of cyclohexane. You will notice that this will cover quite a bit of the lecture because of the various different conformers that are possible for cyclohexane compared to the previous ones, cyclobutane and cyclopropane. We also look at conformers of substituted cyclohexanes. Then we look at isomers and nomenclatures of alkenes. That's a double bond. And lastly, we look at the stabilities of alkenes and alkynes. Notice again, alkynes, that's a triple bond. Alkenes, that's a double bond. So again, for this lecture, you'll need your model set. So I would suggest pause the video, go and find your model set and also your periodic table, and then you can come back. Okay, let's get started. So let us start with looking at conformers of cyclohexane. Okay, so we're looking at cyclohexane here first. And the reason why we're looking at cyclohexane and paying so much emphasis on cyclohexane is because the 6-membered ring is found a lot in nature. Okay, so we'll study that in a little more detail compared to the 4 and 3 and even 5-membered ring. So you may want to get your model set and build your 6-membered ring. Notice that you can actually build a 6-membered ring alkane, cyclohexane, compared to trying to build a cyclopropane because it's very strained. So for cyclohexane, it's not as strained. It is more flexible because of the rotation or limited internal rotation of the carbon-carbon bond. In other words, there is a little more rotation in the carbon-carbon bonds for cyclohexane compared to smaller rings. What you will discover after building it is it's hard to draw, number one, in 3 dimensions. So we have drawn it like this. We're 6 carbons and of course 12 hydrogens. You'll notice that it's possible to have it looking like this, and we call this the chair conformation, or the chair conformer. Why? Because you can see here, this looks like a chair, the way it's built. So here's a chair. And here are the hydrogens. Another conformer is described as the boat conformer, and here's a boat conformer. And of course it gets back down into the boat. So you can see that looks like a boat. So that's why it's called a boat conformer. So these are the two extreme conformers of cyclohexane. One is more stable and the other one is less stable. Let's see why. So now we are defining stability in terms of groups getting too close or how far apart we can get these groups. Notice for the boat conformer, this hydrogen and this hydrogen are extremely close. Well, I would say close. So that presents a degree of instability to the boat conformer. For the chair conformer, there are no hydrogens here that are considered to be close. It's difficult to see how close they are looking at the two dimensions. But once you have built your cyclohexane and form the boat conformer, you will see that these hydrogens get pretty close. And when you do the chair conformer, you'll see that these hydrogens are not very close, even though they look to be very close on paper. Okay, let's go on. So once you have the chair conformer, which is the most stable conformer, notice the chair. What we're trying to do here is this wedge line is trying to indicate in front of the plane, and the rest is in the plane of the paper. What you'll discover is that you can go from the chair conformer to a boat conformer by simply taking this carbon and switching it up to here, and here it is. So now it matches the boat. And then to go to another chair, taking this carbon and just flipping it down, and here it is. So that's the chair. So you can go from one chair to another chair, and these equilibria readily happen at room temperature. So in other words, if you should get a sample of cyclohexane, these equilibria, these two equilibria here are constantly happening, flipping from chair to boat and back to chair. And that's because of the internal rotation of the carbon-carbon bond. Remember again, it cannot rotate as much as your open chain alkanes, but there's limited rotation, and that allows for these different conformations. Okay, let's see here. So let's get back to our chair conformer. Of course, as you imagine now, we will deal with the most stable conformer from here on. Or we will be concerned with the most stable conformer from here on. So let us look at the chair conformer. You will discover that after you've built the cyclohexane, you'll discover that the cyclohexane ring itself, or the carbons in the cyclohexane ring itself, act as a plane. Granted, it's not very flat, but it is a plane. And sticking above are some hydrogens, and sticking in the plane or projecting in the plane are some hydrogens. So since these can be described as two types of hydrogens, we'll describe the ones that are projecting above the plane and below the plane as axial, H8. So there are 6. hydrogens like that. The hydrogens that are in the plane, such as these, we'll describe them as equatorial. As we said in the previous lecture, in the equator, same plane. And we'll describe these as HE. So we have HE and HA for the hydrogens, but we'll use A and E to describe groups in these positions. Okay? So, let us now concentrate on substituted cyclohexane. So let us see which is more stable and which is less stable if we should have a methyl cyclohexane. So notice this is a methyl cyclohexane because all the other carbons here, they have hydrogens, and this is the only carbon with a methyl group. So the question is, will the methyl group prefer to be in the equatorial position as shown here, or in the axial position as shown here? You can take a guess. The equatorial position has more space, and the axial position has less space. In other words, more crowding in the axial positions because of the hydrogens or groups that are surrounding it. So the most stable conformer of a substituted cyclohexane is the conformer that has the group in the equatorial position. Granted, if there's enough energy, and there is enough energy at room temperature, there will be flipping, or there's a flip of conformers to put this in the axial position. So if this goes up, as we have seen here, and this comes down, as we have seen here, this will go from the equatorial position into the axial position. If it's in the axial position, it's closer to these hydrogens here, and of course less stable. Conclusion: if you have a monosubstituted cyclohexane, the most stable conformer is the group being in the equatorial position. By the way, you should be able to draw these conformations using this type representation. So start practicing drawing your cyclohexane rings to show the chair conformer, and make sure that the chair conformer is shown or drawn differently from the boat conformer. Let us look at now disubstituted. So we have disubstituted cyclohexane. In this case, we have a 1,4. So it's a 1,4-dimethyl cyclohexane. Here it is. However, since they are conformers or isomers, they are really different molecules, even though they differ slightly, but they are different. So therefore, we should have different names for these conformers. Let's see how we can name them. Okay, so let's start with this one. You can see that this methyl group here and this methyl group here, they are on opposite ends of the cyclohexane plane. So we describe this as trans. So it's a trans 1,4-dimethyl cyclohexane. This one is a little trickier to see because here's a methyl group in the equatorial position, and here's the methyl group in the equatorial position. But we've seen from the previous slide a ring flip, taking this carbon and flipping it down, and this one flipping it up, puts this group here in the axial position, and this group here, which is in the equatorial position, it puts it in the axial position. So this conformer here is also a trans conformer. So these are two representations of the trans 1,4-dimethyl cyclohexane. Okay? Notice again that this conformer is more stable. Why? Because the groups are in the equatorial position. As you can see here, there are quite a few concepts that you'll have to recognize, and equally important, towards the end of this lecture we'll apply all of these concepts to determine stability of cyclohexane molecules. So this is more stable. Here is something else. Another way of writing the name of this molecule is EE for equatorial 1,4-dimethyl cyclohexane. Okay, 1EE. Or it could be AA for axial and axial 1,4-dimethyl cyclohexane. So you can see here you have quite a few choices in terms of naming these molecules, or these conformers, should I say. Let us look here at another example. Compared to the previous slide, we have switched one of these groups here from the equatorial into the axial. So this one is now an equatorial axial. As we can see here, equatorial axial. This will be the cis because we have just switched one group. So it has to be different from the previous one. So this is the cis conformer. Cis conformer, so it's written as cis 1,4-dimethyl cyclohexane. Or we can say axial for this axial, equatorial for this equatorial 1,4-dimethyl cyclohexane. If we should do the ring flip, like taking this down and then taking this up, we will get this, where this group, methyl group here, becomes the axial, the equatorial, and this equatorial becomes the axial, so it's now axial equatorial 1,4-dimethyl cyclohexane, or cis. Notice it's the same though. So the images of these conformers you'd expect to be the same because the same number of groups are in the equatorial position as in the axial position. Okay, so let us see here. So let us combine what we've learned from the previous chapter. We've learned how to use the dashed wedge. So it is possible to write cyclohexanes or substituted cyclohexanes using the dash and wedge. So this would be trans, right? Because here is a methyl group and here's a methyl group. One is wedge and the other one is dash. So this is in front of the plane and this is behind the plane. Now the cyclohexane ring's plane is in the plane of the paper here. So this is 1,4. Same thing here. We can change these 1,4. Same thing here. Cis on the same side. Or on the same side using a different representation, the wedge or the dash. However, special attention here. However, this type representation, trans and cis, does not tell us if these groups are in the axial or equatorial position. So be careful. If you're asked to show the most stable conformer in which groups are in the equatorial or axial position, you cannot use this type representation. you'd have to use the other one with the chair and indicating the axial and equatorial. So here's a summary. So what we have done so far is a 1,4 substituted cyclohexane. We say, let's start over here. We say that it's trans if the two groups, notice this is disubstituted, if the two groups are in the axial position, it's a trans. If the two groups are in the equatorial position, it's a trans. If one group is in the axial position and the other one is in the equatorial position, it's a cis. Same here. Let's look at the 1,2. So for the 1,2, so what you may want to do is get your model and put a group in a 1,2 relationship, or two groups in the 1,2 relationship, and put one in the equatorial and the other one in the equatorial. What you'll see that is a trans arrangement. When you do the ring flip, you will see that they now become axial and axial, but it's still a trans. Same for the cis. 1,3, this is the relationship, and that's the relationship. So this is a table you may want to keep handy. In the tutorial questions for this week, for next week that I'll give you on Sunday, you will get a good practice, you'll get some good practice questions on using the information in this table. So keep it handy. Let us turn our attention now to alkenes. Alkenes, as you may recall or will recall, has the double bond for the E. So it's a carbon-carbon double bond. When we did that chemistry back in chapter 1, I think, you recognize that this is an sp2 carbon and this is an sp2 carbon, and this is now a pi bond and a sigma bond making a double bond, which means that it's a very rigid bond. There's no rotation about this bond, as you will find for a single bond. So there's no rotation. So once we have groups bonded to this carbon, they are fixed. So we can describe this as a cis-butene because these two groups are on the same side of the double bond, or a trans-2-butene because these two groups are on the opposite side here of the double bond. So you can name these two molecules as trans or cis. Notice before we did this, if you were asked to give the IUPAC name, it would just be 2-butene or 2-butene. But now, because these are isomers, in this case cis and trans geometric isomers, we can indicate the difference in structures based on names. Here's another example. Fumaric acid has the COOH on opposite side, and maleic acid has both groups on the same side. You may recall in biology, these two molecules, even though they have the same molecular formula, they are different, and the body recognizes them as different molecules. Let us look at the IUPAC naming system for this. Okay, so in other words, you can use trans and cis, but you will discover before too long you'll need a better naming system for these molecules. So here is a better naming system for these molecules. It's called the EZ naming system. So let's define it. So first is to identify the carbons of the double bond. So here's one carbon and here's the other carbon. For each carbon, you will have to determine the atomic number of the atom that's directly bonded to it. So let me say it again. So for this carbon, for example, that I'm highlighting here in red, you'll have to determine the atomic number of the atom directly bonded to it. So here's one atom, it's a carbon. So get your periodic table. The atomic number there is 6. And it's also bonded to a hydrogen. The atomic number there is 1. Next, you have to assign priorities based on the atomic number. Carbon, which has a larger atomic number than hydrogen, gets 1, priority number 1. And this gets priority number 2. Okay? You look at the next carbon, which is right here, and do the same thing. The atoms that are directly bonded to this carbon determine the priorities based on atomic number. So the atoms that are bonded to this carbon here is a carbon, atomic number 6, and a hydrogen, atomic number 1. So this gets priority number 1. Okay, here's where it becomes very important. If the groups of highest priority are on the same side, you put a Z. More details is described in the book why it's called a Z. It's from a German name. So you use a Z. If the groups of highest priority 1 and 1 are on opposite sides, we use an E. Okay, so that's why it's called the E and Z nomenclature for geometric isomers. So now from now on, what you'll do if you're asked to give the IUPAC name for this molecule, it will no longer be 2-butene. And you can use trans, but you'll see you'll run into problems for larger molecules. So it's best to use the E and Z, Z2-butene, and this would be E2-butene. Notice the E and the Z are placed in the parenthesis, followed by a dash, and of course the rest of the molecule. Let's look at a couple more examples. Here's another one. So here's our double bond right here. So let's look at this carbon first and the atoms that are directly bonded to it. Let's see if we can determine priorities based on the atomic number. This carbon here has a bromine. The atomic number of bromine is larger than that of chlorine, so this gets number 1. This carbon is bonded to a carbon, atomic number 6, and to a hydrogen, atomic number 1, so therefore this gets priority number 1, and of course since 1 and 1 are on the same side, it says Z. Of course we do know how to name the rest of the molecule based on the previous nomenclature. Same here. This gets number 1, and this is number 1 for the groups across the double bond, and that gets an E designation. Okay, let's continue. It's getting a little more difficult here because if you're asked to give the IUPAC name of this molecule, you could say it is 3-methylpentene, but they are different isomers, or there is at least another isomer of 3-methyl-2-pentene, which would be the geometric isomer. So let's see if we can name this one as drawn. Notice you have to draw this so that you see the geometric isomer difference. So let's start with this carbon. This carbon is bonded to a carbon, and this carbon is bonded to a carbon. So we have a problem because both carbons, they will have the same atomic number. Whenever this happens, you go to the next atom and determine which has the highest priority. The next atom here is a carbon. The next atom here, of course, is a hydrogen. So therefore, this group here gets number 1. And this group here gets number 2. Looking at this carbon, this is, of course, priority number 1, and this is priority number 2. Much easier to see. But of importance here, priority number 1 and priority number 1 are across the double bond, so therefore it gets an E. So pay special attention to that. As I mentioned, the tutorial questions that you will get this for next week will have quite a few examples where you'll have to name molecules looking like this, and you'll have to draw molecules given the names. Make sure you draw it so that us, the graders, can see that they are really across the plane or on the same side of the double bond. Let us turn our attention now to the stabilities of isomers. We'll use this concept here, the energy profile, for an exothermic reaction. If you have an exothermic reaction, you may recall from your Gen Chem, an exothermic reaction is one that gives off heat. So here we start with our reactant, and we carry out the reaction to get the product, so that's the reaction coordinate. It starts off at high energy, and when the reaction is done, it's at a lower energy, so it has given off this heat here. Notice that this heat here is greater than this heat that's given off for the one in black. So what we can say is that this reactant, or these reactants here, are less stable than these reactants. Why? Because we have defined already that anything located in this region of the energy profile is stable, and anything in the upper region, or relatively speaking above, is less stable. So that's the concept that we're looking at here. If you have two reactions that are exothermic and they give the same product, if one reaction, the reactants are high in energy, it's less stable, which means it gives off more heat. If the other reactant, or the reactants of the other reaction, is lower in energy, gives off less heat, it means that it's less stable. So for this, the reactants here is more stable, and the reactants here are less stable. So let's apply that concept over here. Here we have the alkene. This one has a terminal double bond. It's at the end of the chain. The reaction that we'll use, or the exothermic reaction that we'll use, is hydrogenation. In other words, we use hydrogen in the presence of a catalyst. It gives that as a product. Notice it gives off 30.3 kcals per heat. Exothermic reaction. This molecule here is described as having an internal double bond because it's in the middle of the molecule. Same reaction, same product, but it gives off less heat, 26.9. Notice, keyword here, less heat. So based on that, and the concept that we described in the previous slide, you should be able to tell which is more stable and which is less stable. You can tell that this terminal double bond is less stable, and the internal double bonded alkene is more stable. This gives you the energy profile diagram. You can see here that the more stable alkene gives off less energy here, and the less stable alkene reactant gives off more energy right here. So therefore it's higher on the energy profile diagram, less stable. So you should be able to apply this concept to different isomers or geometric isomers of alkenes. Let us look at another concept, and this is the cis and trans arrangement. Is it possible to tell if you have a cis alkene and a trans alkene, is it possible to tell which is more stable and which is less stable? Let's do the same application. Do the hydrogenation, get the same product here. The amount of heat that's liberated gives us an idea. We have more heat liberated here for the cis and less heat, not much, but less heat liberated here for the trans arrangement. Conclusion, the trans alkene is more stable than the cis alkene, just based on this experiment here. So, using the same energy profile approach, we can see that this alkene here reactant is less stable, and that's the cis, and this alkene here is more stable because it gives off less heat, and that's the trans. Conclusion, the trans alkene is more stable than the cis alkene. You may be wondering, why are we emphasizing stability? Of course, in nature, all processes tend to go towards the more stable state. So we need to know what is the most stable state of molecules and how they will react. Less stable molecules will be more reactive than more stable molecules. But we'll get more into that when we look at reactions. Let us see if we can apply what we have learned in a question, in the form of a question. So which of the following alkenes will liberate the most heat upon hydrogenation? In other words, which of the following alkene is the least stable? So this is a question that involves quite a few concepts that we just discussed. So now you'd have to look at each and determine if it's a cis or a trans. Look at each and determine if the double bond is internal or terminal. And based on that, you make a conclusion. Let's look at this. This is an internal double bond. Trans, notice it's trans. The hydrogens are not written in, but they are there. This is an internal double bond. And notice the hydrogen again are there, not written in, but they are there. And this is the cis. Here is the terminal double bond right here. And here's another internal double bond and trans. So let's see. So I would expect that since we know that there's a bigger difference between the heat liberated from the terminal double bond compared to the internal double bond versus the cis and trans, I would think that this may be the answer. Let's see. And yes, it is. So this is a terminal double bond, less stable. It will generate the most heat upon hydrogenation. Notice hydrogenation of all of these molecules here, they give the same product. Okay, let's see what's next. Next here is the alkynes. Which is more stable? You can take a rough guess based on your knowledge of the alkenes. We have two types here, a terminal triple bond and an internal triple bond. Take a guess. The most stable one would probably be the internal. But we can do experimentations to find out which is more stable using the same approach, hydrogenation, a reaction. And here, this reaction gives the same product. And this is 69.2, and that's 65. Less heat liberated here, more heat liberated here. So therefore, this molecule is less stable than this molecule here. So the terminal triple bonded molecule is less stable than the internal triple bonded molecule. Okay, that's the end of this lecture and the end of the lectures for chapter 4. We covered a lot in this chapter. You'll have to take your time and read it through again in the textbook, and make sure you have your model set to build it so you can see the three-dimensional arrangement of these atoms, because when you take the quiz and the test, you will be writing on two-dimensional paper. Again, you are allowed to use your model set when taking the test and the quiz, but you have to be very careful there, because you will have 2 hours to take the test. And if you spend a lot of time building these molecules and turning them, you will not complete the test, the quiz and the exam in time. So make sure you do all the practice before the quiz and the test, especially the test coming up on Thursday. So do a lot of practice, a lot of reading, and make sure you work the tutorial questions that are coming out on Sunday, and get ready for the exam, which is scheduled for Thursday. So continue to study hard, and all the best, and bye.